There is a black hole out there right now, 10 million times heavier than our sun, and it does not belong to a galaxy anymore. It got kicked out. It is moving faster than anything that size has ever been caught moving. Behind it, it is leaving a glowing scar across the darkness, a trail of newborn stars stretching nearly 200,000 light years long, wider than our entire Milky Way, longer than most galaxies are across. And when the people who study the universe for a living first laid eyes on it, they did not believe what they were looking at. Because black holes are not supposed to do this. They are supposed to be the end of the story, the thing that eats light, crushes matter, and leaves nothing behind. Not this. Not a black hole fleeing across the void while giving birth to stars in its wake. So what threw something that massive out of its own galaxy? And what does it mean that we just found proof this can actually happen? Let's start at the beginning, because this discovery did not start with someone looking for a black hole. It started with someone looking for something else entirely. A team of astronomers digging through years-old Hubble Space Telescope images was not hunting monsters. They were cataloging star clusters in a small, unremarkable dwarf galaxy, the kind of quiet, methodical work that rarely makes headlines. And then, sitting in the image, was something that had no business being there. A line, straight, thin, glowing, cutting across the black like it had been drawn with a ruler. The first assumption was boring, and boring is usually correct. A cosmic ray. Charged particles slam into telescope sensors constantly, leaving streaks that look dramatic and mean nothing. Every telescope operator knows the fix. Check the next exposure. If the streak vanishes, it was noise. Move on. It did not vanish. They pulled every exposure of that patch of sky, and the line was still there, in the exact same place, aimed like an arrow at a distant galaxy system nearly 9 billion light years from Earth. It was real, and that made it a problem because nature does not draw straight lines. Galaxies spiral. Gas clouds drift and diffuse. Even the jets blasted out of active black holes tend to bend and fan out over distance. Nothing paints a clean, uniform, 200,000 light-year streak across empty space. Nothing except something moving in one direction, at tremendous speed, for a very long time. The team started eliminating possibilities one by one. A jet from an active black hole, the shape and brightness didn't fit. A galaxy seemed perfectly edge-on, its disk lined up just right to look like a thread of light. Also wrong. Too thin? Too uniform? The light behaved incorrectly for that explanation. Every mundane answer collapsed under examination. What was left was the strange one. A supermassive black hole, somehow thrown clear of its home galaxy, tearing through the space between galaxies and dragging a wake of gas and freshly forged stars behind it. This idea was not new. Physicists first calculated that this should be theoretically possible back in the 1970s. For 50 years, it sat in textbooks as a fascinating could happen. A prediction nobody had ever caught in the act. And now something matching that exact description was sitting in old Hubble data, pointing straight at a galaxy billions of light years away. Hubble had found the streak, confirming it needed something sharper. That's when the James Webb Space Telescope got pointed at the tip of that line. If this really was a black hole punching through gas faster than sound can travel through it, there should be a very specific fingerprint waiting at the leading edge. A shock front, the same kind of pressure wall that builds up in front of anything breaking a sound barrier. Webb's instruments don't just take a picture. They split the light apart and read the chemistry and motion hidden inside it. And what came back was unmistakable. Right at the front tip of the streak, the gas showed a violent, sudden jump in velocity, 600 kilometers per second, packed into a shockingly small region. There is only one thing in physics that produces a spike like that, something enormous, slamming through gas faster than the speed of sound in that gas, compressing it like a wall, everything lined up. The shock's shape, the gas temperature, the geometry of the whole structure. Every piece pointed the same direction. This was, for the first time ever, direct confirmation of a runaway supermassive black hole. Scientists gave it a name, RBH1, Runaway Black Hole 1, a name that assumes, quietly, that it will not be alone for long. Now sit with the numbers for a second, because they are absurd. The black hole itself is estimated to be moving at roughly 1,000 kilometers per second. That's about 2.2 million miles per hour. Something like 3,000 times the speed of sound here on Earth. At that speed, it could cross the distance from Earth to the Moon in about 14 minutes. It could blow through the entire width of our solar system in a matter of days. And based on the length of the glowing trail behind it, it has been moving like this, nonstop, for roughly 70 million years. And it isn't just flying. It's building something as it goes. Stretched across that 200,000 light-year wake are newborn stars, hundreds of them, actively forming right now, sparked into existence by an object that was supposed to be a destroyer, not a creator. To understand why, you have to understand what it's actually flying through. Most people picture the space between galaxies as pure emptiness. It isn't. It's extraordinarily thin, nothing close to the density inside a galaxy, but it's not nothing. There's a faint sprawling haze of gas out there called the circumgalactic medium. Normally, an object drifting through it wouldn't even notice it was there. The gas would simply part around it, the way slow water parts around a stone. RBH1 isn't drifting. It's outrunning the speed of sound in that gas entirely. And when you break that barrier, the medium can't get out of the way fast enough. It piles up in front of you. It compresses. It heats. It forms a wall, a bow shock, the same structure that forms in front of a supersonic jet, or the white wedge of water thrown up by a speedboat moving faster than the water can flow around it. Except here, the speedboat is a black hole with the mass of 10 million suns. Behind it, the opposite happens. The pressure that built up in front collapses once the black hole is passed. The compressed gas in its wake cools. As it cools, it starts clumping together under its own gravity. Given tens of millions of years, some of those clumps become dense enough to ignite nuclear fusion. Stars are born, one after another, strung out behind a fleeing black hole like beads on a 200,000 light-year thread. Stars with no galaxy to call home, born entirely from the wreckage of something running for its life. This is what Webb captured at the tip of that Hubble streak, and in late 2025, the findings were published, giving the world its first direct, confirmed sighting of a runaway supermassive black hole caught by its own supersonic shockwave. Which brings up the real question. What is powerful enough to throw something that outweighs 10 million suns clean out of an entire galaxy? The answer is gravity, but gravity behaving violently in a scenario that only plays out during galaxy mergers. Galaxy mergers are not rare. They're one of the primary ways galaxies grow up. Our own Milky Way has already swallowed dozens of smaller galaxies, and in roughly 4 billion years, it's scheduled to collide with Andromeda. When two galaxies merge, they bring their central black holes with them, and those black holes spiral toward each other, locked in a gravitational dance that can take millions of years to finish. There are two ways that dance ends in an eviction. The first needs a third player. If a third galaxy and its own black hole joins the merger, the resulting three-body gravitational tug-of-war becomes fundamentally unstable. Physics does not allow three massive objects to orbit each other stably forever. What happens, instead, is that two of them pair off tightly, and the third gets hurled outward, flung by the energy stolen from that new pairing, a gravitational slingshot on a galactic scale, almost always ejecting the lightest of the three with enough speed to escape the merged galaxy completely. The second way is stranger, and it doesn't need a third black hole at all. When two supermassive black holes finally collide and merge, they unleash a tremendous burst of gravitational waves, ripples in space-time itself, the same kind of signal LIGO and Virgo detect from much smaller black hole. Collisions, just on an incomparably larger scale. If the two merging black holes have different masses and mismatched spins, those gravitational waves don't radiate evenly in every direction. More energy escapes one way than the other. And in physics, when you fire energy off in one direction, you get a kick in the opposite direction. Newton's third law applied to the fabric of the universe itself. When the imbalance is extreme enough, that recoil kick can exceed 1,000 kilometers per second, launching the newly merged black hole straight out of its galaxy forever. In mid-2026, a separate team worked the problem in reverse, starting from RBH1's known speed and trajectory and running it backward through Einstein's equations using numerical relativity. Their reconstruction was startlingly precise. The two black holes that merged to create RBH1 likely had a mass ratio no greater than about 6-1. The larger of the pair was spinning fast, wobbling on its axis as the two spiraled together before finally colliding roughly 70 million years ago. That specific combination of mass and spin produced a recoil kick strong enough to send the survivor rocketing away at nearly 1,000 kilometers per second. Think about what that actually means. Researchers looked at a faint line of newborn stars in an old photograph, confirmed it with an infrared telescope 1 million miles from Earth, and then reverse engineered the exact spin and mass of two black holes that collided. Nearly 70 million years ago in a galaxy billions of light years away. They are reading the fingerprints of a collision from the wreckage it left behind, and it doesn't stop there. Mergers like the one that produced RBH1 are exactly the kind of event the future LISA mission, a space-based gravitational wave detector planned by the European Space Agency, is designed to catch across the entire observable universe. Calculations suggest a merger like this one would produce a signal in LISA loud enough to be unmistakable. Not a whisper and a shout. But here's the part that should actually unsettle you. RBH1 was only visible because it happened to be plowing through a patch of gas dense enough to light up. The bow shock, the trail of baby stars, all of it depends on there being something for the black hole to slam into. If RBH1 had been launched through a sparser stretch of intergalactic space, there would be no shock front, No glowing trail, no streak for anyone to stumble across in an old photograph. It would be completely invisible. Not hard to find. Actually undetectable, with every instrument we currently have. And galaxies have been merging for over 13 billion years. The conditions that create a runaway black hole, mismatched mergers, three-body slingshots, are not bizarre one-off accidents. They are a natural expected byproduct of how galaxies grow. Which means RBH1 almost certainly is not alone. There should be others. Black holes carrying 10 million, 100 million, maybe a billion solar masses, launched from their home galaxies, and currently crossing the dark between galaxies with no trail, no shock, no signature at all. Silent, invisible, drifting through the void with nothing to give them away. Researchers who confirmed RBH1 flagged this as the next big hunt. Wide-field survey telescopes are the best tools for the job. Instruments already scanning huge swaths of sky, cataloging over 1 million galaxies and counting, with more coming online that will see fields 100 times wider than Webb. The hope is that RBH1 stops being a single lucky find and becomes the first entry in a catalog. Because right now, this discovery only happened thanks to a chain of coincidences. Old archival data, someone glancing at the right image at the right moment, a streak sitting in gas dense enough to glow, a telescope powerful enough and free enough to check. Change any one link in that chain, and RBH1 is still just a hypothesis on a chalkboard. So how many are we missing? We built our understanding of galaxies around the idea that supermassive black holes stay put, anchored at the center, permanent fixtures. RBH1 doesn't overturn that picture. Most black holes almost certainly do stay exactly where they are, but it adds a new category to the universe, the evicted ones. Objects that got thrown out, homeless, dark, and moving, tens or hundreds of millions of years, into an exile with no end in sight. Somewhere out there right now, a black hole with the mass of 10 million suns is moving at 2.2 million miles an hour, dragging a 200,000 light-year ribbon of newborn stars behind it through absolute darkness. Nothing is chasing it. Nothing is going to stop it. There's no galaxy waiting on the other side to catch it. It's just going to keep going. Faster than almost anything else we know of. Into the dark. Maybe forever. And the unsettling part isn't that we found one, it's that finding one at all was mostly luck, which means the ones we haven't found are still out there, right now, completely invisible, waiting for the next telescope, the next archive scroll, the next accident.